Family is already on his way back. And maybe in New Orleans. Sorry, Proctor and somebody make the exam, lost track of the time. Okay. Where is everyone? In the corner. There was a large number of people who didn't want to meet with me today. They had midterm assignments.
Okay.
Okay. So we're testing this too. I'm sorry you don't have a bigger audience. Are we going to record this for posterity from the?
Yeah, I opened the Google Hangout on air. Yeah.
Okay.
Let me see, it's still online.
Set my alarm for the person taking the test. So take it away, I guess.
Yeah, this presentation will be short. So because this is only the project I'm now still working on, I'm still trying to come up with small figures to fill the manuscript for the deadline, which is like on Thursday. So
you're going to send this to
Clear? Yes.
Okay.
Yes. So basically, the topic is about the basic level facilitation in visual object recognition. So I'm talking about object recognition. So basically, what object recognition is in brain. You have an input, stimulus, start from your retina, and it goes to V1. And start from here, the ventral visual pathway, which is the place where you do object recognition, start from V1, V2, and V4, all the way to infratemporal cortex, or IP. That's where the object recognition is achieved in your cortex. And the dorsal stream contains the information of where the object is. So dorsal stream is called what pathway, and the ventral stream is called where pathway, and the ventral stream is called what pathway.
So that's not really true anymore. People now know that that there's representations in the dorsal stream from which the object is decoded. The identity, yeah.
Okay, I mean this is the traditional view of how object recognition is achieved. So basically, people already know that the V1 contains global features. So basically, they are like edges or bars, different frequency and different orientation. So V1 is pretty well understood. And people already know that the IT, the inferior temporal cortex, is more activated for some kind of object categories in specific subregions using IP. For example, this is the right hemisphere. So basically, the right regions, they are more activated for faces than the other objects. So basically, this is called Y space, this is called FFA1, this is called FFA2. They are used for recognizing faces. And of course, there are some other regions, for example, the green one, they are PPA to recognize faces. And also, there's a visual plus one word area, which is more activated for recognizing words. So basically, people already know that. But actually, people have very little understanding of what are the intermediate features between V1 and IT. So people build a lot of neurocomputational models so they basically want to explain what happens in between, and they want to build the models also good at object recognition. So those are just a few feed-forward models, like the HMax in 1999, the VSNAC, and the model by Gary introduced like decades ago, still in development. Those are all feed-forward models. I mean, they already existed for quite a long time. However, people now usually use deep convolutional neural networks as a feed-forward model to model the object recognition pathway in the brain. So everybody already knows that quite well. It's everywhere, like in image classification, video recognition, scene recognition, even in natural language processing. So this is already so basically the deep convolutional neural networks have already been served as a tool, a very powerful tool to solve nowadays computer vision and machine learning problems. That's why everybody is using that, and it's very simple to build because of the whole bunch of packages, libraries like Caffe or Torch available to use. So what's and Google's Tensor, what's the name yet? Tensor something. Yeah. What's more appealing to me is except the fact that the deep networks are very good at computer vision problems, is this one. They learn the features very similar as the features in human visual system. For example, so this slide is from Yano Kun, and basically at the very early layers, we learn the features like the global filters as well as the blob. There are low-level features in the human brain, and also and then in the mid-level features or in the mid-level layers in the convolutional neural network, the features become more complicated, so that they are like contours and they have some shapes of the object. And in the high-level layers, the features are more like real objects. For example, this one is like a bird, and this one is like I think the road or something like that. So basically, there's a gradient of the complexity of the features along the deep convolutional neural network, and more recently, these two guys, Panqu and Van Gerven, they have the very first systematic examination of the predictability of the convolutional neural network for the voxels along the whole ventral stream. So basically, they build a deep convolutional model, and they get the feature map of each layer for their training set, and they want to encode the model and then decode the input. So their result, I will explain later, can account for the gradient of the complexity for the voxels along the whole ventral stream quantitatively, and demonstrated that the convolutional neural networks, it is a very good model of the brain. So basically, the figure C to the right shows that what are the features in V1, V2, V4, and IO means the lateral occipital complex. It's a region that does basic level, a region does general object recognition. So basically, in V1, it contains more low-level features like edge, contrast, and the less high-level features. And in V2, it has more like mid-level features like the contour. And in LO, it contains a lot of high-level features, such as the object parts or the entire object. This is done by analyzing the voxels or the features using Amazon Mechanical Turk. And these two figures shows how their deep convolutional neural network can account for this gradient of complexity of features. So basically, as you can see,
Right. What did they use AMD for?
oh, because they have a lot of voxels that they get from the brain, right?
Yeah.
Yeah, and they have, so basically they want.
I thought they used regression.
Oh, that's for encoding.
What do you mean? Are these like ratings of complexity or something?
Yeah.
By human subjects?
Yes, by human subjects.
Or
And
looking at the features that are in the reverse, the deconvoluted features in the network?
Yes.
Okay.
Yes. And basically, in figure A and B, it shows that, so basically, those colors represent different layers of the convolutional neural network. The blue one are like early layers or shallow layers, and the red one, they are all like higher layers. So basically, they show that the features that encoded in convolutional neural networks, the early layers contains more features in V1 and V2, and the higher layers contain small features account for like IO, the lateral occipital complex, as well as before. So the layer assignment is shown here. So basically, the V1 features, most of them are within layer 1 and 2 because they are blue colors. And for IO features, they are mostly located in higher layers of the convolutional neural networks. So basically, they claim that deep convolutional neural networks can account for this gradient of complexity of the voxels along the whole ventral stream quantitatively. This is only part of their figures. Sorry, this is only part of the results. If you're more interested, you can refer to this paper. And Ben, Vincent, and I also wrote a review a review comment of this paper, and now it's accepted. Thanks. But however, as you can see, those models, so no matter it is convolutional neural network or those traditional models like HMax or the model, most of them has only one feed-forward processing pathway. However, more evidence suggests that a single object recognition pathway is not enough to account for the complexity or what really happens in the inferior temporal cortex. So this is a review paper by Grossbecker and Wiener in 2014. This suggests that so those pictures are all the right hemisphere of the inferior temporal cortex or ventrolateral complex or the ventrolateral cortex. This suggests that there's a transition between the left and right region in terms of the feature map as well as the anatomical properties for the entire IP. And this region, and this device is called middle fusiform sulcus, and it serves as a transition and the device for a lot of functional maps, such as the eccentricity bias. So the left region is more activated for the foveal response, and the right one is more peripheral. And also the left region activates more for phases, and the right region more for phases, and so on. And in terms of the anatomical properties, so for example, the cytoplasmic tectonics, the left region, the density of the cells is much more higher than the right region, suggests that the property of the different regions along the middle fusiform sulcus is pretty distinct. And this.
So wait, so the green in the lower left has a higher density?
Lower.
Lower density.
Yeah, lower density.
So the face
is to the left.
Has a higher density.
Yes.
Okay.
Yes. And also, their findings are also suggested by this guy, Kravitz et al. But in 2013, he proposed that there are actually 6 output pathways in the cortical visual processing, especially in IT. Ben presented this figure. This figure is from Ben. He presented at Penn this June. So all of those evidence suggests that a single pathway is not enough to build a computational model for object recognition. Be good or beneficial if we can incorporate with the guiding principles in the brain, for example, the 2-pathway hypothesis, into training those networks. So if we really incorporate with those mechanisms, maybe we can get better results if we want to train the convolutional neural networks.
Can you go back one slide?
Okay.
So what do you mean by output pathways? Are they encoding different information?
Yeah, so basically here, so this is from Ben's slide actually. So basically there are 6 pathways, and these pathways contain different outputs. They decode different kind of information. Okay. Yeah. Okay, so this is my point, and those are.
But knowing what's coming next, it seems like this is the wrong set of data to show, because you're going to use Moshe Bar's idea, right? Instead of
yes.
This kind of split along the ventral.
Yeah, because I show I show those evidence. It's just to demonstrate the idea that we should not only use a single pathway model. No, okay. I haven't introduced the Moshe Bar's idea.
I want a different network to come after this set of slides than the one you're going to show.
Yeah. So basically, what I'm going to show is about it's something called basic level facilitation, and so here is a brief illustration of what basic level is. So basically, basic level object recognition is when you see something, for example, this one. What's the first word coming to your mind? It should be table. It's not like a classroom table or something else. So basically, there are 3 kind of object recognition hierarchies: the superordinate level classification, and basic level, and subordinate level. So superordinate, like furniture, of fruit. They're pretty generic. And the basic level is the first word that comes into your mind when you want to see something, like desk, table, chair. And the subordinate level is just very fine-tuned, very fine-grained categorization of a specific object. And only expert is more used to say that. So the idea I'm trying to...
Wait, so go back.
Okay.
So you're not mentioning any of Russian principles here.
No, I'll show it later. Show it later here.
Okay.
Yeah, there are actually 4 principles by Russia, right? Rush. Okay. Of what are basic level categories? Basically, there are 4 principles, as Gary already mentioned, already brought it up. So those are 4 of the principles. So first, basic level objects, they have common attributes. And then for basic level categories, they have the same motor movements. For example, chairs. A chair is associated with bending of one's knees. So basically, you will do similar motor movements when you sit on chairs. And then basic level objects have similar in shapes. In shapes, and they have identifiability of average shapes. So basically, when you average the basic level objects together, you still can recognize that as a category.
Principle was that they shared functions as well.
I think it should be. I mean, those are 4 attributes that I have in his paper. Okay. Maybe it's like it's her paper. Yeah. Okay. So go back to Barr's idea, which I want to implement of the basic level facilitation. So this is the idea by Moshe Bar. It's not 2013, it should be 2003. Basically, what his idea is, there are 2 distinct processing pathways in the human brain for recognizing objects. One pathway is very fast, the other pathway is very slow. The fast pathway is called macular pathway, which has a direct connection from V2, V4, the early visual cortex, all the way to the ventrolateral PFC, prefrontal cortex, and the orbital prefrontal cortex. The fast pathway will contains the object related information and can do the basic level categorization in the prefrontal cortex. So basically, for the subordinate level classification, we do that in inferior temporal cortex. But in his hypothesis, and it's supported by a lot of electrophysiology studies, in orbital prefrontal cortex, we actually do the basic level classification. So after we finish the basic level classification, the information of this classification can project back into another pathway that goes from V2 and V4 all the way to IT. So basically, the slow pathway in IT can use the information that is processed by the fast pathway that goes from V1, V2 to the PFC. That's it. That's his basic idea.
So this pathway is literally faster, so magnocellular cells fire more quickly than the ones that mostly innervate the ventral pathway. So they actually attack literally a faster path.
Yeah, because the people already observe the activation in the prefrontal cortex 100 milliseconds after the stimulus onset, but the same signal in the IT appears around like 150 to 200 milliseconds. Okay, so basically, our idea is to apply this this whole notion of basic level facilitation into training deep networks. I have to say in advance that the current implementation of this idea is very basic, and I have a lot of future plans. So bear with me. I want to show a very basic version of this idea. So I first want to choose the basic level categories because we want to do the basic level categorization first. The basic level categories are chosen from the ImageNet 2012 paper, 2012 challenge. Basically, in that network, in that data set, we have, so basically this is a very blurry visualization. We actually have 1,860 scene sets of these whole data sets. So I will show you in a more clear way. Okay, this is not clear, but I will make it bigger. So basically, this is a hierarchy. Okay, so I'll make it. Okay, maybe not see clearly. But at this scale, you may notice that there are like some red nodes and some blue nodes. The blue nodes, I'll make it bigger. Okay, the blue nodes are the 1,000 categories that we already use in the ImageNet dataset. But all of those red nodes, they are 860 in total. Also in the ImageNet hierarchy, but they are not used to train the deep convolutional neural network. So basically, like you can see, this hierarchy is a tree, and each node has a height from height 1 all the way to height 20. So at the very beginning, to choose the basic level networks, to choose the basic level categories, I want to choose like some nodes like have a specific height. For example, all the nodes in this level. But it turns out it's not working because some of the categories, the ImageNet categories, they have a very high height. For example, this one. This is called street sign. And some of the basic level categories, they have a very low height. For example, this one. See dog? Yeah. The dog actually is not that high, although this is a basic level category. So okay.
Has anybody tried just using a network trained on the 1,000 categories to recognize the rest of the categories?
No, not to my best knowledge. I mean, no.
Seems like you're not getting things to try.
Yeah.
That's cool, but how do you add more output nodes and train it? So the network train the output nodes, like you do with Cafe.
Yeah, one thing you could also do during the paper, like, a paper on this to zero-shot learning. So you tell it, then you need to like know what you need, and then you say, I want to classify for everything else, and it can combine to
Yeah, so as you can see, the dog category, basically it has multiple parents. So let's see. Okay, so its parents, it has two parents. One is like canine, let's see. No, this one, canine, and the other is a domestic animal. Yeah, this one. And the dog category has a lot of children. I do count the dog subordinate level categories in the whole ImageNet dataset. It has 119 dog species compared to only 1,000 categories in total in the ImageNet dataset. So basically, it's almost like a dog net. Yeah. So see, this is those are the children of dog, and this one has a lot of children. It's terrier. So basically, it has so many children of sub-dog species. Yeah, and basically, I cannot automatically get the basic level categories from this network, so I have to use the Amazon Mechanical Turk to help me. So let's see where my slide is. Okay. So on Amazon Mechanical Turk, I give them the instructions about what is a basic level category using the the rules by Roche, and they basically categorize those 1,860 nodes or names in the ImageNet, and I get those response, and I resolve those conflicts if they are very close. And so basically, ultimately, I get 308 basic level categories from the 1,800.
Wait, I thought you did that yourself by hand.
And later, I did the Amazon Mechanical Turk job.
Oh.
Yeah.
So, okay.
Yeah.
When did you do that?
Last on Friday.
Right.
Yeah.
Okay.
Last Friday. Okay, so from those basic level networks, from those basic level categories, I trained a basic level convolutional neural network, which has the same structure as AlexNet. So basically 5 convolutional layers and 3 fully connected layers. And I have at the most 4,000 training images per category, because like you said, like we already seen that like the dog category, it may contain so many objects, so it may bias towards that category if we have too many dogs. So in total, I have 700K training images compared to 1.2 million training images for the 1,000 way classification. And I get 81% accuracy on the validation set for basic level classification. And then basically, based on the weights of the basic level network, I just use as is and to train a 1,000 way classification. You can think it as a fine-tune job, but it's not that fine-tuned, because fine-tune usually means you train a very big network using a lot of categories, and you fine-tune on some small data sets, which has much fewer number of categories. But in this way, I start from 308 categories and do the so-called fine-tune in 1,000 way classification job. And I do not change any of the internal network structure. And finally, on the validation set of the ImageNet 1,000 way classification, I get 81.48 accuracy compared to directly train the network using from scratch using the 1,000 way classification. The accuracy is 80.13 using Caffe. So basically, this suggests that the basic level classification can actually help a little bit for the subunit level classification. And also the learned features, this is the fine-tune results on the Cortex 101, this one, on Cortex 256 dataset. So the green one is the fine-tune result using the AlexNet, the trained network, and the red curve is the new network that is pre-trained on the basic level categorization. So as you can see that the very new network actually perform better on the fine-tuning job when compared to the AlexNet. So this suggests the better generalization of the features of the learned network. Okay, so those are some of my results, and basically.
What's the difference between the left graph and the right?
Oh, Cortex 101, Cortex 256.
Oh.
Yeah. And basically, the conclusion is the method works, and it supports the idea of consider the neural mechanisms when training our convolutional deep neural networks. And this is, like I said, it's only a preliminary work of my thesis project. So basically, what will happen next is I will add more figures. Like I want to, for example, for the 308 basic level categorizations, I want to find a way to visualize that, like to compute which level or which height is the most categories are located, and also now I'm in the process of linking with the dark knowledge and the FitNet introduced by Hinton and Bengio, because this is like a two-step training, and they previously have some work on that. to optimize some loss functions, and also to make the network more to be more similar to what Brain does. I may want to add more constraints. For example, the high-low frequency and of the input and the eccentricity bias, or something like that. And my ultimate goal is to use this model, or the final word, the final name is called the deep model, to model some cognitive phenomena, because that's my my work is about. So I want to actually expand Gary's the model to the deep model, and hopefully it can give us more interesting results. Yeah, basically this is what it is. Thank you. Questions? Okay.
Yeah, I want to ask about where does the hierarchy come from?
Oh, I mean this hierarchy, right? Yeah.
I know where that comes from.
Yeah.
But I mean, where?
Really?
Yeah, it's from WordNet.
Yeah, from WordNet.
Oh, I didn't know that. Okay.
Yeah, basically the ImageNet is a subnet of the WordNet. Yeah, and this is from the developmental kit that I also VRC challenge has.
Yeah, I mean, I think it's like in the blank, where the categories.
Oh, yeah, okay. You mean the brain?
Yeah, do they just be words like if you see enough carriers, like it should be a word for the dog. How does that happen?
Okay, I think your question is like, if we do see enough kind of pictures for a specific category, maybe in the brain there will be a fuse from that category area, right? I think this is a very interesting idea. So basically, like some work in Gary's previous paper, if you train a network that it does the expert level categorization task, the activation in FFA will, the FFAs will be actually more separated. The activation will be more separated in that region for the new kind of expert level object you learn. So that suggests that if FFA is a region that does subunit level classification or learn some new, expert level task, maybe you can see some activation in the brain of that's specific to that kind of object category. That's my hypothesis, but I cannot confirm that now. But apparently, this hierarchy does not actually mean that the brain has some region to the very first, which is entity, and some others. I only model the basic level and the subunit level task. Not see everyone. Some of them are too abstract.
I have a question.
Okay.
Can you go to the results on the
Okay.
one? Do you have error bars on this, or like can you normalize it for the number of iterations or talks that you train?
Yeah, I mean that's something I want to add into this result, because I do have the I trained the network actually for several times, and it's pretty stable. Yeah, and the Ukraine iteration versus the error, I will draw that in the manuscript.
So you trained it on the subcategories of ImageNet and then trained it on the full set of
Yes,
right?
yes.
So it means that you're using the same, you use the same data twice to train them.
Not the exactly same data.
But some images were used. Like,
yeah. But they have different output category. They have different output.
Yeah, that's what I'm like. Why do you think that will help to increase like from one person? And why should that help? Because it's seeing the same data, it's the same information.
Not exactly the same information, because the first network is trained for basic level categorization. The learning feature may differ from the subunit level classification. that's the subtle. The difference may be subtle, but
Yeah, I just want to make sense, like,
Yeah.
what's the effect of this? Is this like a
Yeah, I know.
regularization, or I don't know?
That's why I said every other parameter is the same.
I mean, ultimately, it would be nice to have, instead of just two going from one subcategory
Yes.
to the next, just go smoothly and increase the number, and then that would be like,
Yes,
maybe it's better.
right. I mean, that's the next step I'm gonna use is like a real two-pathway model that I hope the basic level pathway, the information can project into the subnet level classification and see whether it really helps. Yeah, that's some idea in FitNet and dark knowledge by Hinton and Vendrell.
So another, the Sunday just sent us the paper about predicting entry level categories. But,
Okay.
another point to make here is that like when Matt Zeeler won the ImageNet challenge, I think he used extra images for training. He had added outside data to the training set. And so he did well in part because he had more training examples. And what's interesting here is you had fewer training examples to initialize the network setting.
Yeah, you can think.
That's an interesting comparison.
Yeah, also I think in Dallas network he has slightly different structure. Not structure, the parameters, because he has like smaller stride in the first layer,
Right,
stuff like that.
But I'm just saying, you know, people augment their training
Yes.
with outside data, and you are actually limiting your training set initially and doing better.
Yeah.
So that's an interesting point.
It would be great if I can try on like VGG or Google Net to see if pre-training on the basic level really helps to improve the performance for 1000 the classification. That would be great if I can try that later.
So, this is better, but maybe because you give them like this structure, like because you train them with basic categories. Is there any psychology work that you guys think is a good idea? Like, it's possible, but I just, when like overdog, and those cat focus, and those scratching, that's the first thing that you say, there's different levels of dogs and stuff. I don't know how it's not something like category or language.
I'm not quite familiar with psychology literature.
Yeah.
But I know there are a lot of perceptual expertise effect, I guess. So maybe you can ask Isabel.
Sorry, what didn't you know to add?
Like, what's the human data? People with basic categories.
Yeah, I mean, I think so, for sure. In fact, they overgeneralize them, so they might call all four-legged things dogs.
Oh, that's it.
And
Can you model it?
what?
Can you just use it as a model?
No, that wasn't the goal here, but if you start to introduce the categories sort of one at a time, that might be some developmentally reasonable idea. I had a, but yeah, we could model developmental processes.
Yes. That's.
One could say it's a really crude model of development.
Yeah.
Yeah, I wonder if it would go the other way. So, like, starting with the 100 category again, and if you're the full classroom with the activation, then you go back to the basic structure to use that and actually
Okay.
if that's the case, then yeah, I mean, you have to expect it to be more the same, and that's why.
And, they have dog as well as, subtypes of dogs as the categories and units have.
Yeah, like I showed.
Yeah, so how do they do that with the software? Because,
They just treat them.
two answers are the same.
Oh, sorry. No. Yeah, there's no dog in the image.
Okay.
There's only subtype of dogs.
We used to have a hierarchical classification to be able to say, I know if it's wrong, not something, but at some point. We got rid of that. Once the
Hierarchical
classification.
classification.
Yeah, so just go as far as we get everyone up.
Is there like a lot of people are still doing that? Will that help?
I think it was in there in 2011 or
Okay.
12 when they operated it, pulled down just to classify all categories and networks.
Okay.
But it's interesting.
Yeah. Okay.
I also think like it'd be cool to pull the hierarchical model, but if the wordnet's not actually ground truth, right? Like,
Yeah.
I'm sure the taxonomy of animals is wrong because people that built it didn't have access to the genetic information to back. And some of the things for them and not just that look at it.
It's gonna be close enough for them. So, I mean,
Yeah,
really,
but apparently I don't know. When we were at Los Alamos, the Australian guy said, wallaby things really do all.
wait, you mean the wallaby, vice versa?
So they're basically randomly distributed between both categories. So it's not that it's and some of the other ones are really like tanks and they got tractor cars, but it's not that we put them.
Okay.